So let's start out looking at some examples just to remind ourselves and build on what we did yesterday. If I have capital F of x equal to the integral from -1 to x of the square root of t squared plus 1 dt, what will the derivative of capital F of x be? Yeah, the square root of x squared plus 1. Okay? Now, again, this is a good one where having this is helpful because we don't know how to find the antiderivative of the square root of t squared plus 1. So this is one of those that we couldn't do using the fundamental theorem of calculus. Okay? At least not with all of the antiderivative and anything. We would have to just make it like capital F of t and work with that, not knowing what that actually was. Okay? So that was easy. This is one, though, that we do know the antiderivative of cosine. What's the antiderivative of cosine? Sine, okay? Now, I want us to, before we jump to conclusions here, what is our initial thought that f prime of x would equal? Cosine of x, okay? Now, notice here, we're not going from pi over 2 to x. We're going from pi over 2 to x cubed. So this is where I want us to actually do all the work and see what happens, okay? So we know that the antiderivative, capital F of t, is sine of t. So we're going to do the integral here by evaluating sine of t from pi over 2 to x cubed. All right? So this is going to be the capital F of x that we're finding. All right? So I have now sine of x cubed minus sine of pi over 2. Now, do we want to, before we go any further, do we want to maybe modify this at all of what it might be? What?
It's not cosine x.
It's not cosine x? What do we think it might be at this point?
Isn't it 3x squared cosine x cubed?
Okay.
Or don't you have to do chain rule?
Okay, so it is cosine of x cubed, and then you're saying use the chain rule? Okay.
Do you not have to use it if it's...
Well, let's actually look and see what she's talking about, all right? That's capital F of x, right? So if I take the derivative of that, the derivative of sine of x cubed, sine is the outer function, so the derivative of sine is cosine. And then here's the chain rule, the x cubed is the inner function. So we do have to multiply by a 3x squared. Okay? What's the derivative of minus sine of pi over 2? It's 0, because that's a constant. All right? So look, f prime is not just cosine x, and it's not just even cosine of x cubed. When you have it going from a constant to something other than just an x, you do plug in whatever that is in for the t, but then you also have to consider the chain rule. When you're taking the derivative, you would then multiply by that derivative of the bound, of the upper bound. Okay? So we end up here with 3x squared times cosine of x cubed. Okay? And that would be our capital F prime of x. That's really the only twist, if you will, in what we're doing here with the second derivative. Okay? Now this one, if you then saw this, this is actually the same one. We need to change that up here. How do you want to change it? Okay.
X cubed and then tangent.
How about if we make it? How about if we make this secant squared? Yeah, that'll be interesting. I wonder what the integral of secant squared is. Okay. Now, is secant squared? Is that defined? Is that defined at pi over 2? Secant of pi over 2, cosine of pi over 2 equals
Well, wouldn't it be
0. So 1 over 0 wouldn't work, okay? So let's make this a plus 0.1. So we're past the asymptote there. And we'll assume x cubed stops before we hit the next one. And we're going to make this secant squared. Okay? So secant squared of t. Okay. And we'll make this 10x cubed just for fun. Okay? So we're going to go ahead and take the antiderivative. The antiderivative of secant squared is tangent. Okay, and that's tangent of t. We're going to evaluate that from the pi over 2 plus 0.1 all the way up to 10x cubed. So that's going to be tangent of 10x cubed minus tangent of pi over 2 plus 0.1. Okay, which we don't know what that is, but remember the point of this is we're now going to find the derivative. Okay, so capital F prime of x, the derivative of this constant part is going to end up being 0. The derivative of tangent of 10x cubed, we have the chain rule, right? Tangent's the outer function, so derivative of tangent, secant squared of 10x cubed times the derivative of the inside, 30x squared. Okay? Alright, now, we can do this using our second fundamental theorem of calculus without all that work, simply by replacing the t. So it's secant squared, replace the t with the 10x cubed, and then multiply by the derivative of that, so 30x squared. Okay, and that's what we had gotten, but by using the second fundamental theorem of calculus, we can do this just writing down the answer. Okay? But that's, like I said, the only wrinkle in this whole thing is that if it's not going to just an x, you need to multiply by the derivative of what it's going to. Yes?
So like on a test, if you were to ask for the integral, or what we just did with the second fundamental theorem of calculus, do you want to do all the work, or can we just replace it?
Unless I told you, show using the fundamental theorem of calculus what this is, you would just write down your answer.
So now we can only assume that it's just replacing of x if it's x to a constant, not x cubed or...
If it's a constant up to just plain x, then you just replace this with the x.
And we don't have to show work.
You don't have to show any work. If it's like this, you still don't have to show any work. You just plug that in for the t, but then multiply by the derivative.
Okay.
Okay? So you still could just write down your answer. It's just you got to remember the chain rule there. Okay. So now we have this example 4. We're going to consider a particle moving along the x-axis where x of t is the position of the particle at the time t, x prime of t is its velocity, and the integral from a to b of the absolute value of x prime of t dt is the distance the particle travels in the interval of time. Okay? Now when we're dealing with the absolute value of x prime, the reason why we have absolute value, it's saying it's the distance. It's not talking about displacement. Remember, the integral of velocity is displacement. the integral of speed, we could say, which remember speed is the absolute value of velocity. The integral of speed would give us total distance, okay? That's really what we're doing here. Because we don't just want how far this particle ended from where it began. Keep reading here. It says here's our position function from t equals 0 to 5. Find the total distance it traveled in the 5 units of time. Okay? Now we're going to need to set this up as multiple integrals because we want total distance, not displacement. Okay? So, how would we figure out how to set this up?
FOIL and multiply the x of t function.
Okay?
Product rule?
To what end?
To what extent?
And then we can take the derivative of it and then take the integral of the absolute value of that derivative.
Do you have to find critical values?
Okay, take the derivative of it, let's find the critical values. Because when will the integral give a negative value?
When we're below the x.
When we're below. So we need to figure out where we're moving to the left and where we're moving to the right. Okay, positive direction, negative direction. Okay? Now, we can't just look at zeros of this. Okay? That would just tell us whether we are to the right or to the left of whatever our zero happened to be. Okay? So we can't just say, oh, t equals 1, t equals 3. Okay? Because we just put some kind of an arbitrary stake in the ground and called that 0. And now we're looking at this thing moving around it. Okay? What we want is when it's changing actual direction. Okay? That's why we have to use the derivative. Now, you can FOIL this out and do it,
Or you can use the product.
or we can use the product rule. I'll go ahead and do this just for practice. The derivative of the first is 1 times the second plus the first times the derivative of the second. Chain rule here times 1. Okay? Notice both of those parts have a t minus 3 in them. So I'm going to factor that out. And then what's left over is the other t minus 3 in the first part, and the 2 and the t minus 1 in the second part. And that gives us t minus 3 times 3t minus 5, if we simplify that. Okay? So that is our derivative, which is the velocity function. Now, we said we need to get critical values. So where are the critical values?
T equals 3 and t equals 5.
5/3.
Good. Are both of those in the interval between 0 and 5?
Yeah.
Yes. Okay, so both of those are going to impact our situation here. Okay? So let's get ourselves a little sign diagram. Look at our velocity from 0 up to 5. We'll put 3 here and 5/3 right here. If I plug in different values into my velocity, if I plug in a 1, I'll have 1 minus 3 is negative. 3 times 1 minus 5 is negative. Negative and negative is positive. So there I'm moving to the right. Now, the reason why I'm doing this, guys, is because I'm going to be taking the integral of that velocity function from 0 to 5/3. What we just did by finding these critical values is we found the boundaries that we would need for our 3 separate integrals.
So you take the absolute value of each boundary?
You can actually, to save yourself time. It's not going to hurt to take the absolute value if it's positive, right? If it's already moving in the right direction, yeah, it's not going to hurt. we're just kind of doing it. If we plug that in, we get negative. So the only one we absolutely have to do it with
Is the middle one.
is this middle one. We need the distance traveled, not displacement there, okay? Because we happen to be moving to the left. And then here we do the integral from 3 to 5. If we were to plug in 4 in our velocity,
It's gonna be
we'd get a
positive.
positive. So here I'm just doing the integral of x prime of t dt, okay? Now, you'll notice here I'm still just writing x prime of t. And that's because I actually don't even need to use this velocity function that we found at this point, because what's the integral of x prime?
X of t, or x of.
X of t, okay? So when I'm doing this, whoop, lost my pen. When I am doing this here, the integral of x prime is x, so this is x of 5/3 minus x of 0, fundamental theorem of calculus.
Yeah.
Okay, plus, now I have the absolute value of x of 3 minus x of 5/3. Plus x of 5 minus x of 3. Notice we have some repeat values in here, so there are some things that we'll only need to calculate once. Okay? So now I just need to go back to the original function we were given, that t minus 1 times t minus 3 squared, and plug in these values. Okay, if I plug in a 0, I get negative 1 times 9, so that's a negative 9. If I plug in a 3, I get 0, so that's kind of nice. Saving the worst for last. I already figured out 3 was 0. So now I plug in a 5. 4 times 2 squared, 4 times 4, that's going to be a 16. So now I just need the x of 5/3. So that's 2/3 times, that's a negative,
It's not going to be negative.
5/3 minus 9/3 is negative 4/3. Squared is 16/9. 16/9 times 2/3
16 and 9.
is 32/27. Okay? By the way, believe it or not, leaving things as fractions is usually the easier way to go. Okay?
Mm-hmm.
So now, we put these together, it's a plus 9, so 9 plus 1 and 5/27, that's going to be 10 and 5/27. That's how far we traveled from 0 to 5/3 seconds.
Mm-hmm.
Plus, the absolute value of a negative 32/27 is a positive 1 and 5/27, plus the 16. So total here, we've got 27 and 10 27s.
Wait, how can you like 0 minus 27, 32 over 27 equal?
The absolute value.
Oh,
We took the absolute value, so now it's a positive 32/27,
yeah,
which is 1 and 5/27.
oh,
Okay. Okay?
Mm-hmm.
All right.